Hello everyone. In this video, I am going to discuss about the definition of complex number. I am going to giving you the idea of the complex set, and then I am going to discuss about the properties of complex set, then different types of operations like addition, subtraction, multiplication over the complex numbers. So let's start with the definition of complex numbers. In the last video, I have given you the idea of the imaginary unit, that is I, and I have also told that why it is important, why I is important in case of complex numbers. So let's see the definition of complex numbers. Number of the form a plus ib, where ab belongs to r is the set of all real numbers, set of all real numbers. A number of the form a plus ib is called a complex number. So any number of the form a plus ib is called the complex number. So the notation used for denoting a complex number is z. So basically we represent it by small z. So that is small z equals to a plus ib, represent a complex number where ab are taken from the set of real numbers. For different values of a and b, we can get different types of complex numbers. Now I am going to represent the set of all complex numbers, which is denoted by C, which represent the all types of complex numbers. So this is the set of all those z where z has the form a plus ib and ab are taken from the set of real numbers. So this C represents set of all complex numbers. So why it is the set of all complex numbers? Because from the definition of complex numbers, we know a and b are the arbitrary real numbers. So if I put arbitrary values of a and b, then we will get the different types of complex numbers, and then it will form the whole set for the complex numbers. So let's take an example. Suppose I am taking a equals to root 3, b equals to 2. Then what is the value of the form of the z will be root 3 plus I into b, that is root 3 plus 2i. Similarly, we can take different values, another different value of a, like suppose it is pi, because pi belongs to r, and b equals to suppose small e, b equals to suppose so minus 7. Then z will be pi plus I into minus 7. So minus plus minus, that is pi minus 7i. This is also the complex numbers. So this belongs to this set C, this belongs to the set C. So for different values of a and b, I can get different types of complex numbers, and this will, the collection of whole the complex numbers will form the set of all complex numbers. Now there are some special names for a and b. So every complex number has the form a plus ib, that there is a special name for a and b. A is called real part of Z and denoted by RE of Z. Similarly, B is called imaginary part of Z and denoted by IM of Z. So why it is real part and why it is imaginary part? Because in case of A, there is no imaginary unit, and in case of B, B is multiplied with the imaginary unit. So this is called the real part, this is called the imaginary part. So any complex number Z can be written as real part of Z plus I into imaginary part of Z. Let's take some example for the real part and imaginary part. Suppose, for example, Z equals to minus 7 plus 3i Z1. Z2 is root 7 minus root 5i. Z3 equals to pi plus I. So real part of Z1 is minus 7 and real imaginary part of Z1 is the term multiplied with I, that is 3. Real part of Z2 is root 7. Now what is the imaginary part of Z2? Because Z2 can be written as root 7 plus minus root 5i, because we had the form A plus IB. So there is a plus, not minus sign. So I have to take minus sign with root 5 only, and there is a plus in between root 7 and minus root 5i. So what is the value of B here? B equals to minus root 5. Therefore imaginary of Z2 is minus root 5. Similarly for Z3, real part of Z3 is pi and imaginary part of Z3 is the number multiplied with I is 1. It is 1 into I, so the imaginary part will be 1. Okay. Suppose I have a given complex number Z equals to A plus IB, and as I told earlier that we can put different values of A and B from the real number set. A, B belongs to R. So putting different values of A and B. So instead of putting different values for B, I fix the values for B equals to 0. So fix B equals to 0. Then Z equals to A plus I into 0. So that implies Z becomes A. Now A is taken from the set of real numbers. So you can put different values of A. And if I put different values of A, that value will be the same for the Z. So that means Z equals to A belongs to R. So for different values of A, I am getting different values of Z. Then we can write any real number in the form of A plus IB, where B equals to, by taking B equals to 0. For example, suppose I have a number 5. So 5 can be easily written as 5 plus 0 into I. Then it belongs to the set of complex number. Similarly, I have a number minus root 7. So it can be written as minus root 7 plus 0 into I. So as we can see from these examples that every real number can be expressed in the form of A plus IB, where the value of the B is 0. Next, I am going to discuss about the different operation like addition, multiplication, subtraction of the two complex numbers. So first I am defining addition of two complex numbers. Addition of two complex numbers. Suppose Z1 equals to A1 plus IB1, Z2 equals to A2 plus IB2. These are the two complex numbers. We have to find Z1 plus Z2. So that means A1 plus IB1 plus A2 plus IB2. So before performing this addition, I am going to tell you about very basic rule. Whenever we are adding these two algebraic term, 3x plus 7y and suppose 5x plus 6y. So how to add these two algebraic term? We take the term along x together and the term with y together. So that means 3x plus 5x plus 7y plus 6y. So it becomes 8x plus 13y. So the same rule we will apply in case of the addition for two complex numbers. That means take the real part all together and take the imaginary part all together. That is A1 plus A2 plus IB1 plus IB2. That is A1 plus A2 plus I into B1 plus B2. So from here we can say the real part of Z1 plus Z2 will be A1 plus A2, and A1 is the real part of Z1 and A2 is the real part of Z2. That means real part of Z1 plus Z2 equals to real part of Z1 plus real part of Z2. Similarly, imaginary part is B1 plus B2, and similarly we can write it as imaginary Z1 plus imaginary Z2. Now I am going to discuss about different properties for a complex set. That is the set of complex numbers. As you can see from this, this is 1, that whenever we are adding two complex numbers, we are getting the form A plus I B. Okay, so this is the form of A plus IB. Then we can write Z1 plus Z2 also belong to the set of complex numbers because it has the form A plus IB, and any number of the form A plus IB is called the complex number. So the complex number set, the set of all complex numbers is closure under addition. So closure under addition means whenever I am choosing two complex numbers and add them, then I am getting the result in the complex number set. The next property for the set of complex number is associativity. So choose three complex numbers Z1, Z2, Z3. So associativity means Z1 plus Z2 in the bracket then plus Z3 is same as Z1 plus Z2 plus Z3. That means if we add Z1 and Z2 first, then adding the result with Z3, is same as if I add Z2 and Z3 first, then taking the addition with the Z1, then they are both same. So how to show this? Take Z1 equals to A1 plus IB1, Z2 equals to A2 plus IB2, Z3 equals to A3 plus IB3. Then add first Z1 and Z2. Adding Z1 and Z2. So we know that this will be the real part, addition of real part plus I into addition of imaginary part. Then take the addition with Z3. So Z3 has the real part A3. These are the real part A1 plus A2. So this will be real part of Z1 plus Z2 plus real part of Z3 plus I into similarly imaginary part of Z1 plus Z2 plus imaginary part of Z3 is B3. Okay, then it is also of the form A plus IB. So this also belongs to the set of complex number. Now we have to do the right hand side. The right hand side is first perform Z2 plus Z3. That is Z2 plus Z3 is A2 plus A3 plus I into B2 plus B3. Then I have to do the addition with Z1. So Z1 has the real part A1 plus real part of Z2 plus Z3 plus I into B1 plus B2 plus B3. So as we can see from 1 and 2 that LHS equals to RHS. Therefore Z1 plus Z2 plus Z3 equals to Z1 plus Z2 Z1 plus Z2 plus Z3. So we can write, so we can conclude from this equality that set of complex numbers is associative under addition. Okay. The next property I am going to discuss is the commutativity. That means I will show the set of complex numbers is commutative under the operation addition. So choose Z1 equals to A1 plus IB1. You have to show commutative. So commutative means Z1 plus Z2 is same as Z2 plus Z1. So this is very easy to show. LHS is Z1 plus Z2. So the addition of real part plus I into addition of imaginary part. And RHS is Z2 plus Z1. Z2 has the real part A2 plus A1 to B2 plus B1, and A2 plus A1 is same as A1 plus A2, B2 plus B1 same as B1 plus B2. Therefore LHS equals to RHS. So the addition is the commutative property for the set of complex numbers. Now I am going to define two new things, that is additive. First I am defining additive identity, and then I will define another new term, additive inverse. So additive identity means, suppose I have a number 2. So what should be added with 2 to get the 2 again? So this is very easy. The value is 0. Any number. Suppose I have the number -7 plus x. This will again give the value -7. So this is the value of x is 0. So I can easily say, in case of R, that is the set of real numbers, the additive identity is 0. So additive identity means the number which is added to another number x will give the value x again. So in case of R, the additive identity is 0. Now as I told earlier, that any number from R can be expressed in the form of a plus ib. So 0 by taking b equals to 0. So 0 can be written as 0 plus I0. So whenever 0 is the additive identity in R, so 0 plus I0 will be the additive identity for C. That is the set of complex numbers. So how to write it? So suppose Z equals to a plus ib, a given complex number. So that let another number z1 equals to c plus id is the additive identity. So the rule says z plus z1 will be again z. A plus ib will be again a plus ib. So the rule for the addition, a plus c, the real part, and the imaginary part, plus I into b plus d, that will be same as a plus ib. So before finding the values for c and d, I should tell how to equate two complex numbers from right hand side and left hand side. Suppose I have two complex numbers, a plus ib and c plus id, and these two are given equal. So when can we say that two complex numbers z1 and z2 are equal? If their real parts are equal and their imaginary parts are equal. That is, z1 equals to z2, where this is z1 and this is z2. z1 equals to z2 if and only if, this is notation for if and only if, real z1 equals to real part of z2, imaginary z1 equals to imaginary part of z2. So from this rule, I can equate the left hand side, right hand side by taking a plus c equals to a and b plus d equals to b. So a and a cancel, so c equals to 0, b and b cancel, so d equals to 0. Therefore additive identity is 0 plus I0. So the next property is additive inverse. Additive inverse. So additive inverse means the number which is added to any number x will be equal to the additive identity. That means additive inverse. So the additive inverse means if any number x given and we have to add another number y to get the additive identity, that means 0. So we can easily say from this that the value of y will be 0 minus x, which is equals to minus x. So in case of addition, the additive inverse is equal to the negative of the given number x. Now, in case of complex number set, in complex number set or in complex set, no, I should write it as, let's start with the value general form z. Let z equals to a plus ib, and let z1 equals to c plus id be the additive inverse of z. So from this rule, or from the definition of additive inverse, this implies z plus z1 will be additive identity. So additive identity is 0 plus 0i. So put the value a plus ib plus c plus id equals to 0 plus 0i. So the rule for the addition, add the real parts and I into imaginary parts equals to 0 plus 0i. Now equating two complex numbers by equating their corresponding real parts and imaginary parts. Therefore a plus c will be, a plus c will be 0, and similarly b plus d will be 0. So we have to find the value of c and d. So c equals to minus a, d equals to minus b. So the additive inverse become, additive inverse for a plus ib is minus a plus I into minus b, or you can write minus a minus ib. So now let's take some examples for the addition. Suppose I have z1 equals to minus 3 plus 9i, and z2 equals to 7 minus 5i. Find z1 plus z2 additive inverse of z1 and z2. The solution. So first z1 plus z2, this is z1 plus z2. So z1 plus z2 is minus 3 plus 9i plus 7 minus 5i. So add the real part plus I into imaginary parts. So this is 9 plus minus 5. So 9 minus 5. This is 4 plus 4i. Now we have to find the additive inverse of z1 and z2. So additive inverse of z1 equals to minus of minus 3 plus 9i, because the additive inverse was minus a minus ib, so we can easily take minus common, so it becomes minus of a plus ib, that is minus of z. So we can find the additive inverse by taking the negative of the given complex number z. So that is negative of the z1 minus 3 plus 9i, that is equals to 3 minus 9i. And for z2, this is minus of 7 minus 5i, that is minus 7 plus 5i.